areas with mixed signs, above and below the x-axis. Welcome, everyone. To begin today's lesson, let's take a moment to reflect on what we have already covered. In our previous lessons, we mastered the technique of using definite integrals to calculate the area bounded by a curve and the x-axis, assuming the function stays on one side of the axis. However, today we are moving into a more complex scenario. A critical challenge arises when the curve, y equals f of x, does not stay entirely above or entirely below the x-axis within our given interval, from a to b. In other words, what happens when the curve actually crosses the axis? That is exactly what we are going to investigate and solve today. Understanding the concept. First, it is vital to understand that in calculus, when we calculate the definite integral of a function from a to b, we are calculating what we call the net signed area. To break that down, think about the position of the curve relative to the x-axis. In regions where the curve is above the x-axis, meaning the function is greater than 0, these areas contribute a positive value to our integral. However, in regions where the curve dips below the x-axis, meaning the function is less than 0, these areas actually contribute a negative value to the integral. This leads to a very important distinction. If we were to simply integrate from our starting point, a, to our ending point, b, without considering these signs, the negative area from the bottom section will mathematically subtract from the positive area from the top section. The result you get is the net area, which is essentially the balance between the two, rather than the total physical area that covers the surface. Since we are dealing with physical area, much like the area of a floor or a piece of paper, it is impossible for an area to be negative. Therefore, to find the true total area, we cannot just let them cancel each other out. We must treat the positive and negative regions as separate entities. We will see exactly how to apply this rule in the next slide. Now that we've identified the challenge, that curves don't always stay on one side of the x-axis, let's dive into the underlying concept of what an integral actually measures. The general rule. Now that we understand why simply integrating from start to finish can lead to errors, let's look at the general rule we use to fix this. If our curve crosses the x-axis and divides our region into two distinct parts, let's call the part below the x-axis a sub 1 and the part above the x-axis a sub 2. We cannot just add them together directly because that negative value will cancel out the positive one. Instead, to find the true total area, represented by capital A, we must take the sum of their absolute values. Mathematically, this is written as A equals the absolute value of a sub 1 plus a sub 2. Essentially, we are stripping away the negative sign from the bottom region to ensure we are adding pure physical magnitudes. In the next slide, I will show you a systematic, step-by-step procedure to apply this rule to any problem. Step-by-step procedure to calculate total area. Now that we understand the theory behind net signed area versus total physical area, let's look at a practical roadmap. To find the total area when a curve crosses the x-axis, you shouldn't just jump straight into integration. Instead, I want you to follow these 5 systematic steps to ensure you don't miss anything. Step 1. Your first task is to find the x-intercepts. To do this, set your function, f of x, equal to 0 and solve for x. However, a very important detail here is to only keep the solutions that fall within your given interval. From a to b, these specific points are crucial because they represent exactly where the curve crosses the x-axis, and more importantly, where the function changes its sign from positive to negative or vice versa. Step 2. Once you have those intercepts, you need to divide the interval. Use the x-intercepts you just found to split your main interval, from a to b, into smaller subintervals. For instance, if you find that the curve crosses the axis at a point we'll call x equals c, you will split your work into 2 separate parts, the first interval from a to c and the second interval from c to b. Step 3. Next, you must determine the sign for each of these new sections. You need to check whether the function is sitting above or below the x-axis in each subinterval. A simple way to do this is to pick a sample value, just any number, from within the interval and plug it into your function, f of x. If the result is positive, the curve is above the axis. If it's negative, it's below. Step 4. Now that you know where the regions are, you can integrate separately. You will calculate the definite integral for each subinterval independently. Don't try to do it all in one single calculation, or you'll end up with the net area instead of the total area. Finally, step 5. Sum the absolute values. After you have your results from each integral, take the absolute value of each one. This step is vital to ensure that every region is treated as a positive value, effectively turning any negative results into positive ones. Once you have all your positive values, simply add them together to find your final total area. In the next slide, I'll give you a real-world analogy to help you remember why this distinction between net and total is so important. Real-world analogy: distance versus displacement. Now, I know that the concept of net-signed area versus total physical area might feel a bit abstract. To make this much clearer, let's step away from the graphs for a moment and use a real-world analogy involving motion. Imagine a person walking along a straight path. First, let's consider the concept of displacement, which is equivalent to the net area we discussed in the previous slides. If this person walks 10 meters forward and then turns around and walks 4 meters backward, where are they relative to where they started? Their displacement is simply 10 minus 4, which equals 6 meters. This is exactly what happens when we calculate a simple definite integral from a to b of f of x dx. The negative portion of the graph subtracts from the positive portion, leaving us with just the net change. Now let's look at the second scenario: total distance traveled, which represents the total physical area. If we want to know the total amount of effort or distance covered, we don't care about the direction, we only care about the magnitude. In this case, the person walked 10 meters, plus the absolute value of the 4 meters walked backward, which gives us a total distance of 14 meters. This is the exact logic we must apply to our calculus problems. When we calculate the total area, we are essentially taking the integral from a to b of the absolute value of f of x dx, ensuring that every movement, or every region under the curve, is treated as a positive contribution. Keep this distinction in mind, because in the next slide, we are going to apply this exact logic to solve a specific mathematical problem. Worked example. Now that we have reviewed the theoretical steps and the logic behind finding the total area, let's apply them to a concrete problem. Our objective is to find the total area bounded by the curve y equals x squared minus 4, the x-axis, and the vertical lines x equals 0 and x equals 3. Let's begin with step 1, finding the x-intercepts. To find where the curve crosses the axis, we set y equal to 0, which gives us the equation x squared minus 4 equals 0. We can factor this quadratic into x minus 2 times x plus 2 equals 0, which tells us that x equals 2 or x equals negative 2. However, we must be careful and look back at our specific interval, which is from 0 to 3. Since negative 2 is outside our range, we only need to focus on the intercept at x equals 2. Moving to step 2, we use that intercept to divide our interval. Our original interval from 0 to 3 is now split into two distinct subintervals. The first is from 0 to 2, and the second is from 2 to 3. Now, for step 3, we need to determine the sign of the function in each of these new intervals. For the first interval between 0 and 2, let's pick a sample point, say x equals 1. When we plug 1 into our function, 1 squared minus 4 gives us negative 3. This confirms the curve is below the x-axis here. For the second interval, between 2 and 3, let's test x equals 2.5. 2.5 squared minus 4 results in 2.25, which is positive, meaning the curve is above the x-axis in this section. Now we reach step 4, where we integrate these two parts separately. For the first area, which we will call a sub-1, from 0 to 2, we calculate the definite integral of x squared minus 4. The antiderivative is x cubed over 3 minus 4x. Evaluating this from 0 to 2, we get 8 thirds minus 8, which simplifies to negative 16 thirds. For the second area, a sub-2, from 2 to 3, we integrate the same function. Evaluating the antiderivative at 3 and subtracting the value at 2, we get 9 minus 12, minus the negative 16/3 we calculated previously. This simplifies to negative 3 plus 16/3, which gives us 7/3. Finally, in step 5, we sum the absolute values to find the total physical area. We take the absolute value of negative 16/3, which is 16/3, and add it to the absolute value of 7/3, which is 7/3. This gives us a final total area of 23/3 square units. As you can see, by following this systematic approach, we avoid the error of letting the negative region cancel out the positive region. In the next slide, we will discuss some common mistakes that students often make when performing these types of calculations. Common mistakes to avoid. Now that we have worked through that example, I want to pause and highlight some common pitfalls. Even if you understand the concept, it is very easy to make a mistake during the calculation process. First, the most frequent error I see is direct integration. This happens when a student simply integrates from the start point, to the end point b, without checking for x-intercepts. For instance, if we had integrated x squared minus 4 from 0 to 3 directly, the negative area and the positive area would have canceled each other out, leaving us with negative 16/3 plus 7/3, which equals negative 3. As we discussed earlier, a negative result like this cannot represent a physical area. Second, be careful not to ignore the interval. When you solve the equation to find the roots, you might find multiple values for x. However, you must only use the roots that actually fall within your given boundaries. In our previous example, we found x equals 2 and x equals negative 2, but since our interval only went from 0 to 3, the negative 2 was irrelevant. Always check your limits. Finally, watch out for sign confusion. It is easy to get caught up in the arithmetic and forget the most important rule. We must take the absolute value of the negative region before adding it to the positive region. Keep these 3 points in mind as we move into our final summary of the lesson. Key takeaways. First, it is vital to distinguish between net area and total area. Remember, if you simply perform a standard definite integral, you are calculating the net area, where the negative regions cancel out the positive ones. However, if you want the total physical area, you must take the sum of the absolute values of those individual regions. Second, always prioritize finding your critical points. Before you even begin integrating, you must find the x-intercepts. This is the only way to identify exactly where the curve crosses the x-axis and changes its sign. Third, let's look at the mathematical way to express this. The total area is calculated by splitting the integral. If your curve crosses the axis at a point, c, you will calculate the integral from a to c of the absolute value of the function, and then add it to the integral from c to b of the absolute value of the function. This ensures every section is treated as a positive value. Finally, always keep the concept of physicality in mind. In mathematics, an integral can result in a negative number, but in the real world, area is a physical quantity. Therefore, your final answer for a total area must always be expressed as a positive value. To wrap up our lesson today, let's review the key takeaways to ensure you have a solid grasp of this concept. I hope this summary helps solidify these steps in your mind. Keep practicing, and you'll master this in no time.